Yeah, so thank you very much for having me. And I know this has been a long day, and I see still faces here, so thank you for staying. And yeah, before I start, I would like to check a little bit, so ask you a few questions. How many have downloaded a neural network math library like PyTorch or TensorFlow and Keras and played around with it? Yeah, that's good. And how many have put a neural network-based service, a commercial such, in production? Ah, there's still some. And in that case, how many have had to come back and maintain this service over a sustained period, like 1 or 2 years? Okay, that's cool. Because if we look at the companies that have this kind of technology in production today, it's mostly like the really big tech giants, and then a few sort of AI startups and some unicorns. But the whole idea is that the big part of companies does not have this technology today. But there's a lot of companies looking into this, seeing the potential and wanting to apply it to their own business. And somehow, when they try, a lot of them get stuck on the road. And I think that has to do partly with, how does this one go forward? Like that? Yeah. So software development and AI development is different. And I'm going to stick my chin out a little bit and say that in software development, we actually know what we're doing. So if it's a known universe, we know what we have, we figure out a way what we want to do, we implement it, and even if it's hard, at the end, we pretty much know the results. So at least they're predictable. When we come to AI, it's not really that way anymore. We take a step backwards. We try to find data that basically illuminates our problem to, enough so that we can actually learn the solution. And that, even if we think we know it's going to work, we still don't know until we've tried. So we need to test everything. And to test an experiment in this case is the data, the model, and how we train that model. And all these parts have meta parameters. So basically, did we do some pre-processing? What model did we choose? How big is it? And how do we train it, learning rate, other kind of parameters we can have. So basically, there's a lot of different things to try. And in order to see if we can do this, we need to try as many ideas as we have, or we can. And the point is, we want to achieve a quick cycle for trying an idea and get some information out there so we can know what to do next. And one other thing is that if you look at these math libraries, they're research software. So they're moving really quickly, and that's really cool if you're a data scientist. If you put it into production, it's not really that cool anymore. But even if they were completely stable, they still require a lot of knowledge. They require infrastructure and tooling around it to actually make sure that you can handle all these experiments, what data was used with what model, with which parameters, as you try these things. And I also think what was said earlier this morning, that how you actually talk around this, how you communicate this, is really important as well. And then it's, yeah. So to really hammer down on that, this being experimental, I'm going to talk a little bit about generating modern dance choreography. I picked this because it doesn't do with images and it's not text. And it's also something that seems pretty straightforward because we have such a thing as an LSTM. It's, do everybody know what an LSTM is? Yeah, well, it's a recurrent neural network, so you have data in, and it goes out, but it also has a feedback loop, so it's an infinite response filter. So what we know of those is that the data that goes back, so the context, is diluted every time. So if you do the naive version, it's not going to have a very long memory. But this LSTM is a version that has a few extra things, so it can have a long short-term memory, and that's why it's called a long short-term memory. So what we try is we shove our data in there, and we try let it predict the next time step. Yeah, how do we get the data, by the way? We put someone in front of a Microsoft Kinect sensor and perform dance for 5 hours. That will give us a 72-dimensional time series with about 500,000 samples. So it's quite easy. You can do it at home. It's not a lot of data, but we'll see if we can do anything with it anyway. So when we try this, by the way, this should really work, right? But it doesn't. If you do this, you will see that it gives you the posture, but it will, when you try to generate, it will just freeze. So what we try instead, we scratch our head, we drink coffee, we talk to our friends, and we realize we're actually trying to model a multi-valued function with mean square error, and that's not a very good thing to do. To give you an idea why is, if you move your arm, and I have a high probability of going up and a high probability of going down, but I have basically 0 probability of being in the middle. If I'm doing this with a squared error, then every time I do a mistake, I will get a super big punishment, so it will actually converge to the very improbable solution in the middle. So we can put in a mixture density network there, so then we actually model the distribution instead. That's much better. The whole thing is that to estimate all these mixtures, we require much more parameters, and everything becomes very large, and we didn't have much data, and this is sort of a bit more tricky to train. So again, what do? Well, we can do an autoencoder. That's a nice trick. So an autoencoder is a learned compression. So we put everything through an information bottleneck. So then the LSTM and the MDM had to deal with a much lower dimensional thing. And this is really good. And we also see that these neural networks are sort of modular, and that's very nice. Wherever we cut in this, we will just find a lot of floats. We don't have to know what they mean, because we can always put another neural network to sort of make sense of it. So it's kind of nice. But it also means more complexity, right? Because now we have lots of moving parts, and we're not going to train all of these together, because that would be slow. So we were going to train the autoencoder first, and then we're going to put the LSTM in there, and we're going to have lots of sort of halfway results that we're going to cache somewhere. And if you're doing this in Jupyter Notebooks, you go up and down, and you change parameters. And if you're a team doing this together, then this, you get the point. So that's why everybody does their own tooling and stuff to keep track of all this. And it's not very nice to have to spend your time on that when you want to spend your time on solving your business goal. But if you actually manage to then, when you're done, go back and see that you can actually re-implement this whole thing and actually get to the same results, then you can get this. So this is after 10 minutes, and this is after many hours. And the cool thing with this is that it doesn't really matter what kind of data we throw at it. If we change Mr. Sticks here for meteorological data, we have to redo everything. We have to train new networks, new autoencoders, new everything. But then we can also predict weather. That's pretty cool. So this is 24 hours in advance. The generated thing is at the top, or the prediction is at the top. The ground truth is at the bottom. So now you come with your Jupyter Notebook to the backend team and the ops, and they will be very happy with you. But that's really not sort of the only big problem. The problem is that usually when you start off, you do a proof of concept, you do it in a limited scope. maybe the data pipeline that you're gonna have didn't exist because you're doing the POC to see if it was actually worth to actually do the other thing. Data is never really clean. You might have missing data or corrupt data. Data is also evolving. There's no such thing as a static data set unless in academia. And so this distribution shifts over time. So do you actually try to figure out when it shifts, or are you gonna periodically retrain your model that has other problems? Say you do real estate evaluation, and the guy at the bank is gonna buy your solution. He sits and checks his own house every morning, and you retrain this model sort of once a week. So he's gonna have, so he's gonna have something that jumps every time you change the model, right? And that's not really what you want. You can also take that as a feature. If you look at Spotify Discover Weekly, for instance, there's a reason why it's called Weekly. You generate a new model, and you don't have to go back and problem solve. And also with this missing data, you might have to develop new models to actually sort of detect corrupt data or impute data on the fly so that you can actually use your model at least in a degraded way. Say you have a lot of sensors and some of them is just not on, but you still need to deliver a result. Or you use satellite images and one is corrupt. And then back to this question, if you have to support this for a long time. And then we're back in that software and AI is not really the same. In software, we have source code. It's understandable, it's maintainable, and, well, sort of, the compilation process is deterministic, so we don't have to rely so much on the compiled binary. When we do it with AI, then training a neural network, a big model, is actually only semi-deterministic. You can try to put all the seeds you want, but you're doing a lot of floating computation on top of each other and in a distributed fashion in parallel. So to get the exact same model is actually, you probably won't. You can get something that is really close, but then you would also want to have the same data or some data that is really, really close, so then you would like to version your data. That can be really difficult as well, as many of you probably know from other situations. And so the thing is, we're more dependent on this actual trained network, so basically a binary blob. And that brings us, it's much more important to actually document the entire thought process, not only to the solution we actually accepted at the end, but how we got there and what we learned during the way. Because in a few years, it's not going to be the same people who developed the first model who works at that company anymore. There might be that a data source that you used is no longer there. You have to switch it out for something else. And then it's really nice if someone has documented this so you can do it from scratch even though you weren't there the first time. Sorry, I'm just going to turn this one off like that. And so this, and I think that this technology is going to be really, really revolutionizing in the coming years. I think it's going to change a lot. But for this to happen, it needs to become much faster and easier to train these models and build them. It needs to become much faster and easier to build AI models that are maintainable. And it needs to be much more easier to the point that companies can have their developers and engineers that they already have doing this. So it's actually you guys in here that is going to do this. We can't expect everybody to become a deep learning expert. That's going to take way too long time. It's actually not going to happen. So because of this, at Peltarion, we're now developing the first operational AI platform. So we're really early in this, so we're just out the gates. But basically, everything I've been touching upon is going to make its way in there. And I would like to take sort of the last minutes to run through a demo of the platform really quick. And to not make this a long thing, I'm going to use MNIST that doesn't even require deep learning, so it's just as a little example, but at least it will give you sort of an idea what this is. Yeah. So let's see if we can get out here. Here. Yeah, so I'm going to log in, so I'm actually going to do this live. See if I'm going to fall on my own sword here. So basically, you can be in multiple. I'm going to make this a bit smaller. Is this still visible to everybody? Yeah? Cool. So you can be in multiple organizations, and you can make projects. Actually, this is not good. This is better. So let's call this Codiax. We'll go in. Oh no, we'll go in, go to the project, upload a data set. Here I can upload stuff. I can also import from a URL, which is what I'm going to do. So I have a little URL here with MNIST, like that. And this is also a collaborative platform, so it's meant that you can be many people in this at the same time. Let's see if we can get to the next. Yeah. So in here, I can choose. Now it's just 2 features, so it's not very much. But I can choose that this is a categorical, and I can sort of create what features I'm going to use in my model. So I can call this label and make another one that we call image. And now I'm gonna save this version, and that's actually that's equivalent to a commit basically. So now that everybody else who's on the platform can use this, if they change the data set and do their own changes, anything I do that relate to this data set will be the same. And now I can go and model. So I'm going to make a new model here. And it has the data set, the version, training and validation set that it split for me. And I can now start to build a little neural network, since it's a really easy thing. It's just MNIST. I'm not going to do too much. So this is a very bad network. It's as I can make these a little smaller. But it still gives me a bit of information of what I'm doing wrong. I'm going to say it's categorical cross entropy, and that I'm going to use a softmax. So now I can train this. Let's go for a bit fewer epochs, and off we go. And now, even if someone else is doing this, I can actually, as I said, this is completely collaborative, so I can, if I go into another here, I can duplicate this. And so if someone else is in there, then they will see if I move around, it will move around the other one. So I can, if I'm a team, I can see what my teammates are doing. And I can copy their work, sort of branch off. And they can even copy stuff and put in their experiment. So that's basically cherry picking, if you want. And I know seems really scary because there's no code. But it turns out that the code that you're writing when you're doing this is actually very much declarative code, and it's not very nice to write. It's a bit error-prone, and the thing is here that you can be quick and lazy and just go around, and you don't touch the codes, you don't introduce any bugs, and the code underneath can be clean, so you don't have to trace back and make sure that you actually didn't do any mistakes. It keeps track of what you're training on and so on. So you can just, here we can see results of the first one, and we have the other one that's coming soon. And you can go on and see sort of the accuracy. This first one that just had the pixels straight, it's not very good. If we see the other one that had convolutional neural networks, it's a little better. And I think maybe let's be happy there. We don't have to go any further. And at this point, we can then go and deploy this. So we create a new deployment. We select this V2 experiment. And we say that we want to enable deployment. Yes, we don't want to change anything more. And here we got a curl command, so we can actually try this model, which, of course, we should try. So let's see. We're going to have this part. I don't know if this is visible to you guys. So here we go, and I think I have an image here that's called 3 underscore dot JPEG. There we go, and then we need the rest of this, which is our token and the path to the experiment. And there we go. There we have a prediction. Now that's not super visible, so my friend Daniel made a little, made a little classifier app where we can just copy and paste these things. And here we can actually use, just make sure it was called image here as well. Yes, it was. And here we can drag an image and see what the network, it thinks it's a 3. Cool, we can invert it. Yeah, it's still a 3. If we tilt it, now then it's a 4. We can try another number. Yeah, it's a 4. Let's not invert it. Not grayscale. Yeah, it's a 4. Yeah, so everything that was done in there is completely versioned in all ways, so that is fixed. Yeah, I think that was everything. Any questions? Yeah.
Second for the microphone.
Hello, thanks for the presentation. I have a question. How would you approach debugging? I mean, for instance, you have this model. It was the inverted 3. It thought it was 4. How is it working? I hope so. How would you approach debugging without code in your platform, codeless debugging? Because I think you want to maintain that fashion.
Yeah, thank you. I think that's a really, really good question. And I would split debugging into 2 things. Because one is when your code just doesn't run, and that kind of debugging we don't really need now, because since if we build the UI correct, then you won't really have to go in there. But when you do neural networks, the much worse is that it's actually running, it's training, it's learning, but you have no idea whether it's doing anything useful. I mean, how good is it? There are pretty good, I mean, you should have in practice to actually set what you expect out of a sort of business value when you start. So how good do you need to be before it's worth doing, and how good, well, basically when should you stop? Because otherwise a team of data scientists will just keep on doing until they can't get it any better. But the debugging part there is to see what the network actually does, and to try to give you ideas of, are your layers too small, are they too big, or what is it actually looking for in the input, so you could basically grad cam and these kind of things. We have, this is very much on the roadmap, so it's not really in the platform yet, but it's coming. And we're having a few master thesis students working on this as well. So hopefully we'll get, the idea is to have basically several run modes. So one where you train it, where it's optimized and runs as fast as it can, and one where you can say that I want to do this in debug mode, and then get out sort of much more information out of the neural networks. That will slow it down, so you don't want to do it all the time, and it will also generate copious amounts of data, so you will basically want to do it for small things. But say you see your training goes really nicely, and then it starts to wobble a little bit, and then it explodes, then you can sort of go back to your previous checkpoint and debug from there. That's what we aim to put in there for her. Yes?
Thank you. It's quite interesting, although for a data scientist it feels a little bit like we are just drag and dropping. But what about pre-processing the data? Because that's actually a big part of the job.
Yeah, I mean, of the total job, that's a super big part of the job. And when we started in 2004, the software that we had then was very much more geared towards pre-processing, slicing, dicing, and trying to, basically that whole part of it. Now that we're redoing this in the cloud, we're basically, we have to start somewhere, and we start where there is no real other solutions available, and then we're going to expand in both directions. So pre-processing is definitely coming, along with much better sort of, all the visualizations and those things, and data mining parts in the front end.
And what about pre-trained models for feature extraction? Could I use that?
Again, do you?
Is this working? Pre-trained models for feature extraction.
Yeah, pre-trained. Yes. Right now now I built the model myself, but there's a concept called snippets. So if you want a ResNet 50 or a NASNet or something like that, you don't have to build the whole thing. And that's also going to come with pre-trained weights. And so right now you can sort of train your own network, but that's going to be, of course, quite expensive because it takes a lot of time. But right now you can do that, and you can sort of take a part of that network and copy it to a new experiment. And actually, copied weights like that will also be versioned, and so you will know what experiment they came from.
Okay, thanks.
Okay, fantastic. Thank you very much for joining us here.
Yeah, thank you.
So, with that, also we are at an end for the day. So I want to give a big thank you to all of the organizers. So Vlad, Oana, the whole team who put that together, a lot of volunteers. A lot of them are not here anymore. They're already on their way to Sibiu because we do another day tomorrow in Sibiu. So that's why we can't call everybody on stage, because most of them are already gone and on their way there. And I want to thank, of course, all of you for coming here and making that possible, as well as all the sponsors who enabled us to pull this conference together. Again, there are still volunteers outside with tablets asking for your feedback to see what we can do better next year, what kind of speakers you want to bring, and what kind of other improvements you want to have. As well as I shared earlier, you can go to techsylvania.com to see about the tech conference next June that we're bringing together. So with that, thank you very much, all of you, and I'm looking forward to see you again soon. Thank you.